Good morning, students. Due to the unfortunate situations, we don't have contact classes. We'll try to finish the syllabus through making small videos so that you can listen to them, and we'll try to finish the module and your syllabus as well. And if you have any doubt, I'll inform you that during some time in a week or every day at particular times we can meet over GoToMeeting or other apps. I'll let you know where we can meet, or you can directly mail me if you have any doubt in anywhere. I'll start with module 5 because module 3 the derivation parts are there, so I feel that module 5 will be easier for you to understand. The content is familiar to you. Drift and diffusion current in semiconductor. Drift current we have already done. Hall effect and its application, and magnetoresistance. Hall effect you have done. The experiment PN junction also you have done. VI characteristics you have done. Direct indirect band gap semiconductors are a new topic. I'll let you know what it is. Then photodiodes, LEDs, solar cells. You know these devices and their construction and how they work, that are going to learn in this module. What I'll do is I'll make small videos which will be easy for you to watch and to understand, maybe around 10 to 15 minutes videos, and we'll try to cover this in 4 or 5 videos. We'll try to finish this module. Now the first thing is drift and diffusion current. As you know, the current is flow of charged particles. In semiconductors, two types of flows are possible. One is called drift current. Drift is nothing but when you apply external force, that is external potential difference or electric field, charge carriers will flow in the influence of this, under the influence of this external field. Electrons will flow exactly opposite, whereas holes will flow in the direction of the applied field. This kind of flow will give rise to current, is known as your drift current. Whereas diffusion is a different phenomena altogether. If somehow you can create a higher concentration of charge carriers in one particular place, they will try to diffuse through the material to the lower concentration region. For example, if you take photodiodes, when you shine light on it, suddenly there is a increase of charge carriers at that point. So these charge carriers will try to diffuse, and while they diffuse, they will flow from one point to the other. This will give rise to a current that is known as your diffusion current. Drift current, just now I told you that holes will move in the direction of the field, and whereas the electrons will move opposite to the applied field direction. So these are the directions. Like if you take at a very microscopic scale, like you want to observe each electron, their direction will be very haphazard because they will be bouncing back and forth. The electrons will be traveling in valence conduction band, whereas holes will be moving in the conduction band. So they will be bouncing back and forth with various things. So there will be like instantaneous energy velocity that will be different. But when you take about the net movement will give rise to the current that we see in the due to the applied field. And this average movement or average motion or the flow of the electron is known as your drift velocity, because velocity is characterized by speed, and the general notation is Vd. V subscript d, with the units are like centimeter per second. So drift velocity will be the same for electron and hole, because if electron is moving, the hole will move exactly opposite to that in same speed. Now this is a schematic of understanding. If you have a semiconductor and you let the current flow through this, you created a potential difference between these two terminals, then the charges will flow. Okay. Holes will flow in this direction, electron will be exactly opposite direction. This will give rise to current. And we talk in terms of current density because this is a more generic term, that how much current is flowing per unit centimeters. That's what the unit of current density is, amperes per centimeter square. So how much it is flowing through that. If you know what is the charge of this, if you know what is the concentration, how much concentrated they are, and you know what speed they are moving, you can know what's the current. So the current density or the drift current density is nothing but the charge times the concentration times the drift velocity. So T is the concentration for holes, N is the concentration per electron. They can be equal or they can be different based on what kind of semiconductors you are talking. So that's why we always tell that there is a hole drift current density, electron drift current density. If it is intrinsic, it will be same. If it is extrinsic, the N type will have more drift current due to electrons, and P types will have more hole drift current due to holes. These things we have done, but I'll just brush through it. This drift velocity is nothing but the mobility of each electron or each hole times the applied field. So if you replace that here, what you'll get is your current density is equal to charge times concentration of the charge particle times the drift mobility of that particular particle times the applied field. Okay, so for electron holes it will be P, and electrons it will be N, and electron mobility and hole mobility will be different because they will be moving in different band. So from this you can find out the resistance and conductivity also from Ohm's law, that is current density is equal to conductivity times the applied field, or applied field divided by the resistivity, that will be the current density. If you equate these two are same, if you equate the current density and the current density that we get from the mobility of the charged particles, both the particles, you can find the relationship between your conductivity and the mobility. So this derivation we have already done, so I'll not go into that, but I'll just tell you the conductivity will be the charge of the particle, because both electron and hole have the same charges, so times your mobility of the electron times the concentration of the electron times mobility of the holes times the concentration of the holes. The conductivity will be exactly 1 by resistivity. Now coming to the diffusion current. So diffusion current, as I told you, it's a different times. This is a different kind of current flow. This is due to the concentration gradient. Like there is a difference in the concentration of the charge carriers. If there is a certain range in the charge carriers at one particular point, then that will try to diffuse throughout the material or diffuse to the lower concentration region. So that will give rise to current that is known as a diffusion current. And diffusion, it depends on the what kind of material it is. So you have a diffusion coefficient also. So the diffusion coefficient, or the diffusion is described, or diffusion of the flux is, or the particle is described as your diffusion coefficient into the change in the concentrations. If you talk about holes, then diffusion coefficient of the holes times the concentration change times your charge will give you the diffusion current density for holes. The same is true for the electron as well. There is a change in the sign because they will be moving in the opposite direction. Now the total current will be the current due to the drift as well as due to diffusion. So for hole there is a kind of diffusion, the drift current is there, and the diffusion current also. So if you add these two, that will be give you the current due to holes, and the same is true for electron as well. The total current will be current due to the holes and current due to the electrons. Now we'll go to the next topic. This is called Hall effect. Hall effect, it was discovered by Edwin H. Hall in 1879. What it says is, if you have a semiconductor or if you have a current carrying conductor, and which is placed, if the current is flowing in this direction, which is placed in a magnetic field which is exactly perpendicular to the applied field direction, then exactly perpendicular surfaces like this and this surface, there will be a potential will develop, and that potential is known as your Hall voltage, and this effect is known as your Hall effect. Now this happens because of your Lorentz force. If your I current is passing through the semiconductor and it is placed in a magnetic field of B, then the charge carriers will experience a force F, which is in the perpendicular direction both to current as well as the applied field, and this is given by that F is equal to QE plus V cross B. So Q times E plus Q times V cross B. Now this E, the whatever the force they are experiencing along this direction, this is because of the Hall voltage, and we'll distinguish that using a EH or different notation for the field that is due to the Hall voltage. Now the deflection due to the magnetic force or the magnetic deflection force, how much deflection happens due to the magnetic field, if it is given by Q times VD because it's a drift velocity, you are applying some current, so it's a drift velocity, and B is the field. And as the Hall voltage is developed, it will be exactly opposite to that, because there is a potential development, so there is a field, so the Q will experience the charge, the force due to that also. These two will be at a equilibrium when you have a when they reach, like, the force, it will not just pull it away, but it will reach to an equilibrium. So at that point, what will happen? Q VD B equal to Q EH. So if you cancel the Q both sides, it will be EH is equal to VD B. VD is nothing but your drift velocity, and we know the drift velocity from your drift current density is equal to charge concentration times your charge times your VD. If you substitute the value of VD from that equation into this, what you get, EH is equal to J by NQ times B, where J is current density, B is the field, N is the concentration of charge carrier, and Q is the charge. And the relationship between Hall voltage and Hall field is Hall voltage by the thickness of the, or the distance between the two surfaces of that semiconductor, that will give you the Hall field. Now one more parameter that characterizes semiconductor is known as your Hall coefficient. Hall coefficient is nothing but the ratio of Hall field divided by the product of current density and magnetic field. So whatever magnetic field you applied times current density, if you divide it EH, if you divide by this quantity, that will give you RH value. Again, we know that EH from the previous slide, it's JB by NQ. If you substitute this here, it is nothing but 1 by NQ. N is the number of charge, or the charge carrier concentration, Q is the charge magnitude of the charge. For N type semiconductor, because N is small n is the concentration for electron, and E is the charge of electron, and charge of electron with a negative sign, so you have a negative 1 by Ne. And for P type electron, 1 by Pe. P is the concentration of hole, and E is the charge of the holes. What all we can know from this Hall effect? Hall effect, we can from the sign itself, we can know what is the sign of the charge carrier, whether it's an N type or P type. If it's a negative, it's N type, positive means P type. Hall coefficient or Hall effect can be used to measure the drift velocity. If you know the concentration and charge, and you know the current density, you can find out what is the drift velocity. You can know the field, the B is already how much field if you apply, if you know the RH value, and just substitute the current density and other things, you will get the B value. Mobility of the charge carriers can be measured by the conductivity of the material and the Hall coefficient. So you can find out this mu is equal to EH value from the RH value, you can find out. Hall effect can be used to measure the number of charge carriers per unit volume, like RH is equal to 1 by NQ. If N goes here, then 1 by N times 1 by RH times Q will give you the charge carrier concentration. So that's all for now. We have learned about drift and diffusion current. We have learned about Hall effect. In the next class, we'll learn about this magneto resistance a little, then we'll learn about the other things. Thank you.